Okay, so thanks everybody for coming. Really excited to kind of get the Fermi Gym started. I'm James Jamona. I got my physics PhD in 2020, and I've really been wanting to practice my own order of magnitude estimation. And so I thought that like making a little community, finding some other people to practice with, um, would be a great way of like keeping myself, sticking to that habit. And I also, I'll kind of talk, throughout these few slides, think that this is a really um, kind of, it's a skill that I don't think is taught enough or practiced enough. I think it's a really powerful and general skill. So the idea of the Fermi Gym is something like kind of a workout class, something that there's no real pressure to go to, but that you can kind of go meet some friends and together do something that's a little challenging. It's not supposed to be easy. You're supposed to feel the burn, but like over time, you kind of build up your confidence, build up your skills, build up the kind of challenges that you can tackle. The agenda for today, I've got some slides. I wanted to talk a little bit about, why I decided to set this up and why I think order of magnitude estimation is really powerful. Then we've got some warm-up problems. These are, hopefully going to be pretty easy, mainly just to practice unit conversions and like working with kind of scientific notation and powers of 10, just to get everybody, their juices flowing. And then we're going to have two kind of group problems. I'll split us up into breakout rooms, and then we'll convene and like discuss how different people approached the problem, broke it down, and like made progress on it. And one of the big ideas here is that like we gotta really work on and practice not being afraid to like say I don't know and not just give up right then, but to push, to try and grab knowledge from like any place you can use it. Different kinds of bounds, intuitive gut feelings, bring all this stuff together and like keep making progress on these problems, and also practice taking something that looks really big and complicated and breaking it down into smaller pieces that you can get a grip on and then recombining those. So it's totally okay to make mistakes, totally okay to say like I don't know how to fully solve this problem, but like what we're practicing here, the reason it's like a gym is that we're trying to work out, we're trying to like push our limits, push our comfort zone farther and farther each time. So I have like a kind of a fun little story where I realized that this was a skill that like I wanted to develop more, and more importantly, that there was kind of something missing in my physics education up to that point. So this is a picture of a really cool, exhibit that an artist I like set up. Olafur Eliasson made these waterfalls around New York City, including this one on the Brooklyn Bridge. And his idea of like why he set this up was that he had been, thinking about landscapes and thinking about how it's really hard to tell how big some mountain is or some cliffside is if you just see it. But if there's a waterfall on it, that really helps kind of tell the scale of what you're looking at. If the waterfall is like making it all the way to the ground, it's not that big. If the waterfall is kind of making it a third of the way down and then breaking into mist and like the water's not even reaching the ground, then that's like a really big cliff. And I was telling one of my friends about this my senior year of undergrad after I had studied a bunch of physics. And he asked me like, okay, well, James, like how long like can a waterfall fall before it breaks up into mist? And I was stumped. I had no idea how to solve it. I was like, well, I guess you'd have to use like fluid equations and solve something or other. And I don't know how to do it. And, I was kind of shocked that I had no idea how to make like some progress on this problem. And it wasn't until a few years later in graduate school that I took an order of magnitude estimation class, and I learned like the right way of solving that problem. And it's not necessarily like writing some complex equations. Yeah, so I forgot that I had this slide. So, you know, the waterfall coming down and breaking into mist. And so like how long does it take before it breaks into mist? And the answer is that there's actually like competing effects between like air drag on the water and surface tension of the water. And you can like estimate surface tension of the water. We're going to learn how to do this in like future lessons by knowing like hydrogen bonding and like energies of water molecules. You can figure out like air drag, and it's like that process that sets this like this scale of the water either staying together or breaking up into molecules. And I was just like, I was amazed that I had never kind of learned to approach problems in this way before, kind of taking some like deep, simple models of the world and being able to apply them like in the real world in these like complex domains. And so the way I like to think about what we're doing here at the Fermi Gym is like normally when you learn to do math or science or reason, you know, there are these paths with these guardrails. You know, you learn to apply this equation in this situation. You learn that like some expert calculated some answer to some question you might have, but there's kind of like narrow domains of knowledge and certain paths that you're supposed to follow. And what I want us to be able to do is like go off on our own paths and like ask any questions that we want to ask and not have to wait for some expert or somebody else to figure out, you know, what the answer is and for us to look it up, but instead to just feel confident and you know, have the tools to be able to like go anywhere we want and, you know, and ask any question we want and kind of have some idea of how to make progress on that. So, you know, to talk about a little bit, oh yeah, so Venkat asked in the chat, are there any tool recommendations, or should we be keeping a paper notebook for this? And certainly, I think when we get to the questions later on, definitely having a pen and paper. You know, everyone should be like kind of working. That's part of the practice. You know, you have to put in those reps. You actually have to put pen to paper and actually try to solve these things. I am going to kind of highlight some different quantities. I think probably you should maybe memorize or keep top of mind that like show up a lot and are useful later on. So, you know, maybe if you want to write down some cheat sheet of some of those, but for the most part, yeah, pen and paper, and maybe just keeping track of questions you run into that you don't know how to solve. Then we can like discuss them and tackle them together in future gym sessions. So coming back to this slide. So there's kind of some various concepts that I think are related to how you kind of tackle any problem. And like several of them seem really simple, but they're actually like deeply powerful. And so one of them is actually just like knowing a lot of different units or like, you know, physical quantities for things. So knowing that like power is in watts and what that means, that's like an energy per time. Knowing, you know, different kinds of lengths, different kinds of volumes, different, you know, ways of approaching densities. And one of the like interesting things about units is we've got a lot of different units. We have like imperial units, we have like the metric system with kilograms or grams, you know, we have MKS and CGS, and there's all these other weird units, angstroms and Sverdrups and all this stuff. And the reason that like there's a proliferation of units is that those different units are like good in different regimes. They're kind of like the right tool for the job. And so we should be comfortable grabbing like the unit that's closest to the problem and then like converting it to other types of units to combine knowledge together. And so you don't have to like memorize, you know, the value of everything in one unit. You can use, you know, if you're more comfortable in miles than kilometers, just like remember the answer in miles, and then, you know, you can convert it later on. And so, you know, that's totally fine. We want to just make it things like as easy as possible to remember and like derive from and jump off from and connect. Another thing that, you know, we're not really going to focus on today, but I think is very, you know, one of the things I really want to practice more often is these ideas of dimensional analysis and scaling. And so the idea here is that you can, start a problem and you can ask what like units is the answer in. Maybe it's a power, an energy per time, or maybe it's a length, maybe it's some distance, or maybe it's a surface area. And it's going to have some like, uh, unit type, quantity that the answer's in. And then you ask like, kind of what quantities do I have to start with? And what are some ways I can combine different things together? And usually you can get the right form of combining those initial quantities together to find the answer without, just by kind of making the units match. And it's really amazing. You don't get constants, right? So if it's like pi r squared for the area of a circle, you'll figure out that you need an r squared, but maybe not get the pi. But like that's, gets you a lot of the way there. And if you're looking at scaling, if you're saying like, how much more area does a small circle have than a big circle? A lot of times those constants cancel out. And the scaling properties usually you can figure out just by doing dimensional analysis anyway. So that's really powerful tool we're going to kind of dive into. And another thing, I think one of the biggest like ideas here is this idea of connecting the atomic scale to the human scale. So like knowing a little bit about the size of atoms, the energy scales of atomic and molecular interactions lets us like answer a whole bunch of like human scale questions about the densities of metals, of rocks, of gases, of speeds of sound in different materials, the yield strengths of different materials, like, and knowing those kind of things like yield strengths, we can figure out how tall can mountains be before like the gravitational weight, equals the strength of rock. How tall can buildings be? How strong is steel? How tall can trees be? Like all these kind of human scale questions fundamentally come from knowing about atoms and kind of atomic scale processes, because like everything's made of atoms. So we're gonna like really practice, making reasoning, making those connections and going back and forth there. And finally, there's kind of some other types of reasoning and tools that I feel that I first encountered when doing order of magnitude stuff. And these are things like understanding, latent heats of vaporization and specific heats, types of, diffusion, thermal diffusion, viscosities, and kind of mean free paths through systems. And, a lot of questions you might be interested in oftentimes are physically grounded in some of these kinds of quantities. So anyway, so that's a lot. That sounds like a lot. And don't worry, we'll like build up over time and we'll practice together and we'll learn to like be deeply familiar with a lot of these ideas. So the last thing I wanted to do before we all start doing problems together is kind of give one example of an order of magnitude question I solved. So you guys, if you haven't seen something like this before, can kind of get a feeling for, how sloppy to be and kind of the, that we're not trying to be rigorous here. We're trying to be fast and loose. And really quickly, just as a reminder, order of magnitude means that we want to get within a factor of 10 of the right answer. And so if like, let's say the right answer is like 50, we'd be happy with anything like less than 500 and anything over 5. So you actually have like a factor of 10 on either side. You have like a range of like 100 of like getting to the right answer. So like, we're not worried about, being precise here. We're just trying to get within the ballpark. And so, one question that I like, I'm very proud of that I kind of got close to the right answer was asking how much does the atmosphere weigh? I was driving up with Bethany and her family to the Mauna Loa Climate Observatory, and we were kind of reading on Wikipedia about various layers of the atmosphere. And she saw on Wikipedia that it had the weight of the atmosphere, and so she asked me how much could I order of magnitude it? And so, there's a lot of different ways one could approach this. And, if you guys want, you can maybe think about yourselves how you would set this up, how you approach how much the atmosphere weighs. Often, something people like to do is think about like, the atmospheric pressure per some area, and then multiply that by the area of the Earth, because pressure is like a force per area. That force is coming from the weight of the atmosphere. So like you can do that over the surface area of the Earth, get the weight of the atmosphere. But I kind of did a very sloppy way of getting the answer here. I was thinking, all right, are there any things I know that have to do with weights of like gases or weights of things in the atmosphere? And one thing I knew was that humanity puts out like gigatons of carbon, of CO2. That's like the kind of right unit for how much every year civilization makes of CO2. And so I said, okay, we're probably putting out tens of gigatons per year. And over the last 200 years, we've altered the amount of CO2 by like a third. And so, let's say that total the amount of CO2 is like 1,000 gigatons. So that was just me kind of ballparking, trying to get nice, easy numbers. And so, 1,000 gigatons, 10 to the 3 for 1,000. Giga means billion, 10 to the 9. So together, that's about 10 to the 12 tons. And I'm showing you this here because this is kind of how I want you guys to also approach all these problems, right? Very quickly, we want to get into scientific notation. Yeah, we also like if 3 times 3 is 10, like 3 divided by 2, like those cancel out. You're like being sloppy, or you're just trying to ballpark stuff and go quickly. So anyway, 10 to the 12 tons of CO2 in the atmosphere. And I also knew that like, the amount of CO2 in the atmosphere is a few hundred parts per million. This has like gone up over time. I think now it's around 400, but I just said to make the numbers easy, 400 is about 1,000. Let's say the amount of CO2 is 1,000 parts per million. And 1,000 parts per million is 1,000, 10 to the 3. Parts per million is 1 in a million, 10 to the minus 6. So together, that means that the weight of CO2 in the atmosphere was about like 0.1%, 10 to the minus 3 of the weight of the total atmosphere. So if the weight of CO2 is 10 to the 12 tons, that means that the weight of the total atmosphere was 10 to the 15 tons, and a metric ton is 1,000 kilograms. So another 10 to the 3 there. The weight of the atmosphere, I estimated at 10 to the 18 kilograms, and the real answer was 5 times 10 to the 18 kilograms. So, that's kind of, what it looks like, to be doing order of magnituding. And so now I have some warm-up questions for everyone. So, I will end recording